My name is Julia Bryant. I'm here in the Astrophotonics group, but also in the Zipper Astronomy group. Integral field spectroscopy is basically like a three-dimensional view of a galaxy, where in two dimensions you're looking at the spatial dimensions of the galaxy. In the third dimension you see the spectrum at every single point, or pixel if you like, across the galaxy. In order to be able to do that, we have developed a new device here in the Sale laboratories called a hexabundle. A hexabundle takes 61 optical fibres, and at one end they are fused together using a very special process which was done with the machine behind me, in which we can lightly fuse the fibres to form a bundle which has very high field fraction, so greater than 75% field fraction, which is 50% more than any other imaging fibre bundle in astronomy in the world. But at the same time, we prevent what's called focal ratio degradation, which causes a loss of throughput. The hexabundles have been deployed on the 3.9 metre Anglo-Australian telescope near Coonabarabran. We have an instrument called SAMI. So SAMI is an integral field spectrograph that feeds the AA omega spectrograph. And the advantages of SAMI are that we can put 12 hexabundles on the one instrument to look at 12 galaxies simultaneously. So this means we get a three-dimensional cube of each of those 12 galaxies all at the same time. And we can do this time and time again, night after night, and amass a very large sample of galaxies. So the SAMI survey is planning on observing 3,600 galaxies. It's already done more than 2,200 to date. So there are 140 people in the SAMI survey team that are using the SAMI Galaxy survey in order to be able to do their science. And personally, I also use the SAMI Galaxy data to look at the difference in rotation of gas and stars. This tells us quite a lot about how gas gets accreted into galaxies. If gas is rotating with the stars, it means that the gas was likely generated by the stars in the galaxy. If the gas is not rotating with the stars, it is likely to have come in externally from the galaxy. And so by looking at how the gas is misaligned to the stars in different types of galaxies and in different environments, we can actually use the SAMI data to work out how galaxies of different types grow their mass. And growing their mass through accreting gas is very important, because accreting gas also feeds star formation in galaxies. And then we can compare how galaxies look today with different morphologies, different types, if you like, from disks to spheroids, and how they could have got to look like that given the history of how that they have accreted their gas. Back here in the labs, we're developing new hexabundles. So the new type of hexabundles, the next generation hexabundles, will have much better packing of the fibres, regular packing, but more importantly, they'll have a lot more fibres. It will no longer be 61 fibres. There'll be anything up to 200 or more fibres per one bundle. What this does is give us a physically larger bundle, but also means that we can observe out to a larger region on each galaxy that we look at. These new bundles are being developed for the next dark time instrument on the AAT, which is called Hector, and that is a new generation instrument with feeding brand new spectrographs that is going to be operational on the AAT in 2019. This will amass a very much larger galaxy survey of tens of thousands of galaxies, which will give us an enormous amount of information to statistically detangle the processes within galaxies and relate them back to the merger history of those galaxies in different environments.